All right, in this video we're going to talk about antiderivatives and the process of finding antiderivatives. So a function, capital F, is an antiderivative of lowercase f on an interval if f capital F prime is equal to lowercase f. Below we see a couple of examples of antiderivatives of x squared, and you'll notice that what they all have in common is the 1/3 x cubed, but they all differ by constants. And that's because constants vanish when you take their derivatives. And you can see that graphically what that means is they're all shifted vertically. But shifting a graph vertically doesn't affect slopes, so we expect all of those to have the same derivative. Okay, and so you'll also notice that when we find antiderivatives, we put a plus c. So when you find antiderivatives, you're finding a whole family of functions whose derivative is whatever you are presented with. All right, so this leads us to something called differential equations, which is an entire field unto itself. And just to define it, it's an equation that has a derivative in it, basically. Okay, and there are many types of differential equations. In our course, we're going to look at a few techniques for some basic ones. To solve a differential equation is to find the original function whose derivative is involved in that equation. And there's a general solution, which I will highlight here in yellow. A general solution always has the plus c, and then there's a particular solution, and the particular solution can only be found if you're given an initial condition. An initial condition would be a point. Okay, so some point has to be provided. So here's an example. So solve this differential equation, f prime of x is equal to 3x squared plus 1. We want to find the general and the particular solutions. Okay, well, so f prime of x equals 3x squared plus 1. Going forward, you'll see we start to use this notation, which it's sort of optional, but it can be helpful. So we use the integral symbol to indicate we're going to take the antiderivative of both sides of this. And so the antiderivative of f prime is f. And the antiderivative of 3x squared is x cubed. The antiderivative of 1 is x. And now I throw in a plus c. And I've now found my general solution. Oops. I have now found my general solution. Okay, so there's my general solution. But I got to find my particular solution, and in order to do that, they have to provide me with a point. So this is enough to find what that c should be. Okay, so the general solution is here. That's the whole family of functions whose derivative is 3x squared plus 1. Okay, that's the general solution. So the particular solution would be whatever we get for c when we plug in that point. Okay, so if f of 2 equals -3, using my general solution to the left here, I know that if f of 2 equals -3, then when I plug in 2, and I get 2 cubed plus 2 plus c, that needs to equal -3. And this is enough to help me lock down that c. So this is 8 plus 2 plus c equals -3. So that's 10 plus c equals -3, or c equals -13. So that my particular solution would be f of x equals x cubed plus x minus 13. And now I have my general solution and my particular solution. All right, let's try another one. So different notation, but same process. It says dy dx equals cosine of 2x. Later on, we'll talk more about this idea of what's called separation of variables. This equation only has x involved, right? It says dy dx equals cosine of 2x. But what's typically done in preparation for this notationally is you move that dx over there so that you write dy equals cosine. I'm just going to indicate that that's the whole input, 2x dx. And then you're taking an antiderivative. When you take the antiderivative of dy, you're going to get y. And then we got to focus on the antiderivative of cosine of 2x. So this is y equals, All right, so the antiderivative of cosine is sine, so I'm going to start with a sine of 2x. But if you check, the derivative of sine of 2x is going to be cosine of 2x times 2 because of the chain rule. I don't see a 2 above, which must mean I need a 1/2 here, plus c. Now we're asked to find a particular solution, and right now I have the general solution. So to find my particular solution, I am going to plug in my initial condition. Okay, that's my initial condition, and an initial condition is enough for me to solve for that c. Okay, so y of 0 equals 1, so y of 0, in other words, when I plug 0 in for x, I get 1/2 sine of 2 times 0 plus c, and I need that to be 1. This becomes sine of 0, that's the y-coordinate on the unit circle when you've rotated 0, so this is 0, so I just get c equals 1. And so my particular solution is y equals 1/2 sine of 2x plus 1. Okay, that function's derivative is cosine of 2x, and it goes through the point 0, 1. There's another example just written out. It's really no different, just a written out process. One last point I guess I'll make is that you can always check to see whether a function satisfies a differential equation. Solving differential equations turns out to be a really hard process. But if I give you a differential equation, which this is, and then I ask you, is this a solution? Right? Is this a solution? You simply just need to see if it works, right? If it solves that. So what I mean by that is I'm going to take this e to, so y equals e to the x, and the claim here is dy dx equals y. In other words, it's a function that's its own derivative. So what there's many ways to do that. I'm going to substitute e to the x in for y. So now this reads dy dx is equal to, and I'm going to put a question mark here because I'm trying to figure out if my original equation here on the right makes this true. So let's check it. Let's deal with the function provided and take its derivative. Well, dy dx is equal to, well, the derivative of e to the x is e to the x. And what do you know? That's precisely what we see here on the left. So yes, it is. Okay, so yes, y equals e to the x is a solution. Okay, an alternative way of showing that is, you could just look at the red branch here. Dy dx equals e to the x, which is y to begin with, right? So dy dx indeed equals y. And we'll finish with this one. Let's see. Is x squared e to the x a solution to this differential equation? I'm going to take this and put it in for y so that it's all in terms of x. So this reads dy dx is equal to 2x times y, which is x squared e to the x, or in other words, 2x cubed e to the x. So the question is dy dx equal to 2x cubed e to the x? Well, here's our function y. Let's go check. I'm going to take its derivative. Now I got to use the product rule here, so that's 2x e to the x plus x squared e to the x. And I can factor out a e to the x and write it like this. Okay, now there's really no way to convert this thing in blue, this thing on the right in blue, into what's here on the left. So it's not, right? So this is clearly not the same as that coefficient there. And so the answer is no. Y equals x squared e to the x is not a solution. That was sloppy. Okay, so there's just a brief introduction to differential equations, and we'll do obviously more examples going forward.